Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 1 on Introduction to Functions. Unit 2 is all about functions because they serve as really kind of a building block for almost everything that we do in Algebra 2. Now much of what we're going to do with functions, especially at the beginning of Unit 2, should be reviewed, but probably, from Algebra 1. You didn't do a lot of function work in geometry, or you actually did function work, but just didn't probably realize it was about functions. So let's jump right into it and start talking about what a function is. The definition of a function. Now the concept of a function, which you studied in Algebra 1, is very important at all levels of math. When the value of one variable can be predicted based on the value of another variable, we say that there is a functional relationship between the two. The following definition of a function is amazingly important, so let's take a look at it. And let me move my little pen icon off of there. Let's take a look. A function is a rule that assigns exactly one output value, a y value, for each allowable input value, typically an x value. These rules can be expressed in different ways, the most common being equations, graphs, and tables of values. We call the input variable independent and the output variable dependent. Now, let's talk a little bit about this before we kind of hop into our first exercise. A lot of people will sort of like ignore this definition and they'll kind of get this kind of hazy but somewhat useful definition of a function in their head. But look, at the end of the day, it's this simple. A function is just like a black box, and you put a value of x in and a single value of y comes out for that value of x. You never put a value of x in and get two values of y out, just one value, all right? Function rules can be sort of abstract. They can have nothing to do with reality. It could just be like, hey, take the input and double it, or take the input and paint it green and then, put shoes on it and send it along on its way. Again, the key is whatever goes in, a single thing comes out for that particular input. All right? Also, this kind of terminology about independent versus dependent variables, again, that's a little bit misleading. What's independent, what's dependent? But the idea is, right, we've got one variable, right, that can kind of freely change on its own, and the other variable will depend on what that input value is. All right, that being said, let's take a look at exercise number 1 and work with a particular function. A music service offers a plan whereby users pay a flat monthly fee of $5 and can then download songs for 15 cents each. Letter A, name the independent and dependent variables in this situation. All right, well, think about it for a moment and see if you can write down what you think is the independent thing in this situation and what the dependent quantity is. Pause the video now. All right, well, the independent variable, which is going to be somewhere here, is the number of songs that are downloaded, right? That's the thing that can be kind of whatever it wants to be. I download 0 songs, I download 20 songs, I download 5 songs. That's independent. What is dependent, on the other hand, is the total amount paid in a month, right? That is going to depend on how many songs we download, right? And if I say I've downloaded 35 songs, right, that's my input, there's only one output that's going to go with it, right? It would be like a weird music plan if you were like, well, I'm going to download 35 songs, and the output was, well, you're going to pay $12.50 or you're going to pay $22.75, right? No, right? There's going to be only one output that goes with that input. Now let's take a look at letter B. Using the information supplied, fill in the table below for various values of the independent input variable. All right, so songs downloaded is going to be X, monthly cost is going to be Y. Now, one thing that should be pretty easy is if we download no songs at all, 0 songs at all, right? We've still got to pay that flat monthly fee of $5, and so therefore our output is going to be $5. Okay, that's going to be it. Now, what I'd like you to do is take a moment and think about what your monthly cost would be if you downloaded 10 songs. Pause the video now and see if you can figure that out. Well, of course, the way that's going to work is I would have to take my 10 songs, multiply it by 0.15, which would actually give me 150, and then I'd add it to my original $5, and I'd have to pay $6.50, right? That would be how much I'd have to pay for 10. So I'd get $6.50, all right? Why don't you go ahead and see if you can fill out the rest of these values. Pause the video now and go ahead and do that. All right, well, for 20 songs, we would do 20 times 0.15, right? 15 cents each is $0.15 each. I would do 20 times 0.15, I'd actually get $3. I'd add that to the $5 and I'd find that there was an $8 charge. For 30, I'd do the same thing. I'd get $9.50. For 40, I'd get $11. And for 50, I would get $12.50. All right. And in each case, what I'm doing is I'm taking the number of songs, multiplying it by 0.15, and then adding on that $5 flat fee. Okay, which leads us very nicely to letter C. Based on your work from B, write an equation that relates the number of songs downloaded, X, to the monthly cost for the user, Y. In other words, I want an equation now for my function. Y equals what? Pause the video now and see if you can write this down. Well, you just have to think about what you did up here, and instead of using 10, 20, 30, 40, 50, you use X. So what did we do? Well, we took 0.15, we multiplied it by the number of songs that we downloaded, got that amount of money, and then we had to add it to 5. So there's our equation. Now what I'm trying to illustrate here are different forms that functions can come in, right? Functions can come in table form. Here's a good example of that function being shown in the table. Functions can come in equation form. There's a good example of showing that function in an equation. And now let's take a look at it in graphical form, letter D. Create a graph of this functional relationship on the grid provided for x greater than or equal to 0, less than or equal to 100. Well, you already have tons of great points, right? You could plot 0, 5, right? You could plot 10, $6.50, 20, $8, 30, $9.50, etc., right? You may want to figure out what the plan costs when you download 100 songs, all right? Because then you could plot that somewhere out here. But why don't you go ahead and plot all of these points, and that should give you a good start on the graphical representation of this function. I wouldn't use your graphing calculator to graph it. That seems like a little bit of overkill. All right, well, if I plot all of these points, and also just, when x is equal to 100, let's say, y would be equal to 0.15 times 100 plus 5, which would end up being 20. But if I do that, then what I end up getting is I end up getting that graph, right? So all of these points that I've actually got marked along the graph come from this table. And then that point out there at 100, 20 is that final value that we had. All right, now one last little thing, because we always want to throw out questions that make you think a little bit. Letter E. Are there any values on the interval 0 less than or equal to x less than or equal to 100 that don't really make sense as input values? Explain. All right, well, pause the video now and think about this a little bit. Well, what goes to the heart of it is what x represents. X represents the number of songs that you've downloaded, right? And yet, from 0 to 100, there's lots of values, in fact, an infinite number of values that x could not be. So really, any value that is not a whole number. Any value of x that's not a whole number, right? X represents the number of songs. Downloaded. So, gotta get some more room here. So cannot be fractional. Now, as an aside, what that really means is that actually the graph isn't entirely correct. All right, really, the graph should not be drawn as a continuous line. There should just actually be little dots at 0, 5, 1, 5:15, 2, 5:30, etc. All right, but oftentimes in real sort of like world problems, even if x can only be whole numbers, they will still draw this as a continuous line because it still gives you the information that you need, which is how does the cost, of this plan depend on the number of songs that you've downloaded. All right, let's keep working with functions. Here we go. There are relationships that are functions, and there are relationships that aren't functions, right? So there are relationships between two variables that are functions and ones that aren't. It's important to be able to distinguish between when a relationship is and isn't a function. So let's take a look at that in exercise number 2. The set of points -1, -5, -5, 8, 4, -2, 0, 7, and 10, -2 gives y as a function of x. All right, simple enough. Letter A. What is the output of this function if the input has a value of -5? All right, well, pause the video now and go ahead and answer this relatively simple problem. All right, well, now this is key, because when I look at these points, I see a -5 sitting right here, and I see a -5 sitting right there. All right, the key is, which one of those do I work with? Well, if the input has a value of -5, that means x is -5. And what I want is the output, and that's y equals 8. Right? So it's really important when functions are given as coordinate points, especially, it is really critical that you understand and that you remember that the input is the x variable and the output is the y variable. And that's also true of graphs and equations, but it could be easily confused right here. Let me just erase that so it doesn't get confusing. All right, letter B. In a function, can different inputs have the same output? Well, take a look at this particular example where I tell you y is a function of x and see what it tells you. Absolutely. Yes, in fact, in this particular example, when x is equal to 4, y is equal to -2. And when x is equal to 10, y is equal to -2. The definition of a function says every input, x value, has exactly one y value. The definition of a function in no way, shape, or form implies that every x value gets a unique y value. That is not in any way in the definition of just your garden variety function. All right. Now finally, let's take a look at letter C. Explain why adding the point 4, 7 to this set would mean that it no longer represents a function. Why don't you go ahead and think about that? All right, well, it's very, very simple. If all of a sudden, this point was sitting there, then when x was equal to 4, y would be equal to -2 according to this particular pair. And when x was equal to 4, y would equal 7. In a function, a given input can have only one output. There it is. That is, again, that is the most important thing about functions. For a given input, there's one and only one output. So you can't have 4, -2 and 4, 7. A lot of students will kind of circumvent all of that and just say x can't repeat, which is fair. X can't repeat, but y can in a function. Fair. Again, a little limited, but whatever. All right, let's take a look at a graphical representation of some functions or not functions. I don't know. Let's take a look at exercise number 3. A small plane takes off and records its height as a relationship, notice relationship instead of function, between its horizontal distance from the airport's radar tower, that's in figure 1, and as a relationship with how long it's been since it took off, and that's figure 2. All right? So let's kind of like take a look at this for a moment, right? So it takes off, represented at point A, and then at point B is some other time, you know? Anyway, and you can kind of see it, right? You know, a plane takes off and then maybe kind of circles back before it kind of like flies up in the air. That might be what's kind of going on in figure 1, right? And in figure 2, right, because this is the horizontal distance that the plane is from the airport. All right, this one on the x-axis is the time since the plane took off, okay? So let's answer some questions now about this. Letter A, and we'll come back up to the graph in a moment. At what height or heights is the plane at when it is at a horizontal distance of 450 feet from the radar tower? All right, well, why don't you go ahead and answer that question. When the plane is 450 feet from the radar tower, horizontal distance, at what elevation at what height or heights is it at? Go ahead and pause the video now. All right, well, here's 450 feet. If I simply go up and kind of look at my graph, it is at a height of 100 feet and looks like 150. All right, again, that's perfectly fine, right? The plane takes off, it's 450 feet from the airport, then maybe it kind of like circles back. You know, 450 feet horizontally from the airport and 100 feet above the ground. It kind of like then maybe starts to circle back. It comes back to 450 feet from the airport, but now it's at a height of 150 feet. It's all good, right? Letter B. At what height or heights is the plane at 25 seconds after it's taken off? All right, this is simple enough. Why don't you go ahead and answer that question? All right, so 25 seconds after taking off, here's 25. I go up, and it looks like it's 200 feet above the ground. All right, great, awesome, whatever, just graphs, you know. Letter C. In one of the two relationships, the height of the plane is a function of the input variable. Explain which is a function and which is not, and give a reason for both. All right, I'd like you to think about this for a moment, and then we'll talk about it. All right, well, figure 1, right, is not a function, and figure 2 is a function. All right, and now let's talk about why. So figure 1 is not a function because we could have two different heights for a given horizontal distance. And again, this is important Because if I said to you, what height is the plane at when it is 450 feet away from the airport, right? You couldn't give me a clear answer. You'd say, well, you know, it was both at a height of 100 feet and at a height of 150 feet. And that's not saying it's at two heights at the same time, because the input variable here isn't time, right? It's how far horizontally the plane is from the airport. And you know, you could have a plane that does this, right, as it goes up, and it could hit a different height over and like you could have different heights over and over and over again for some kind of horizontal position that it is above the ground. On the other hand, this is a function because for any given time, the plane has only one height. In other words, you can predict the height of the plane if you know the time after it took off. You cannot predict the height of the plane if you know its horizontal distance from the airport. That is not a functional relationship, and this is. All right. Now, this leads us to one of the most famous tests in all of work with functions, helpful graphical test. You can easily tell if a graph of a relationship is that of a function using what's known as the vertical line test. A graph represents a function if any vertical line drawn on the graph passes through the graph at most once. All right? And we'll talk about why this works, but let's just take a look at these two particular graphs. This is the graph of a function, and this is the graph of not a function. If I take this vertical line and I start moving it through this graph, then at no point in time does it hit the graph more than once. On the other hand, if I bring this vertical line over here, right, there are many instances, like let's say right here, where it hits the graph multiple times. The reason that the vertical line test works is because along a vertical line, all the x values are the same. So at that particular x value, which is around x equals 2.5, because I stopped it at a weird place, we end up having a y value down here at around -10, a y value here at around -4, a y value here at around 2, and a y value of here at around 7. Doesn't matter what exactly the y values are. The problem is for that particular x value, there's more than one y value. On the other hand, if I bring this particular vertical line, if I can even grab it, apparently I can't anymore, it's decided that it doesn't want to move. If I bring this vertical line over here, and I stop it, let's say at x equals -3, there's only one y value. There's only one output. All right, so the vertical line test is very, very helpful. If a vertical line hits the graph of a relationship at most once in any given location, it is a function. And if it hits it multiple times, it's not a function. All right, let's wrap this up. So functions are absolutely huge, and we're going to be studying all sorts of different functions. Linear, quadratic, trigonometric, exponential, logarithmic, I mean all sorts of different functions. But at their base, it's very simple. Whatever the function type is, whatever it's modeling, whether it's real world or abstract, for a given input, there is at most one output. And we played around with that in a variety of ways in this particular lesson, right? And we even introduced that nice graphical test of it right at the end, which is really helpful if you have a graph. If you don't have a graph, it's not quite as helpful, all right? But make sure to learn that fundamental definition of a function. Given an input, there's at most one output, all right? Because we're going to be coming back to that time and time again. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.